Hello everyone. My name is Kushal Modi, and today I will be talking about the advances that are done in the deep learning field based upon medical image analysis. So this is a field. So when it is kind of applications of deep learning in the field of medicine or like medical images. So and how the analysis could help and outperform the current technology that we are using for medical images. We are going to talk about that. This is a project for my this is a short story assignment for my class CMPE 297 advanced deep learning. And without wasting any time, we would let's directly jump into that. So, as you can see, so the abstract is as many people know, employing super deep learning based approaches for clinical picture assessment has evolved into an important study topic both in healthcare business and academics due to the growth of artificial intelligence and notably the latest breakthroughs of deep learning. So the as everybody knows, it is the deep learning is the industry is booming right now because of the recent breakthroughs, and as we are catching up with the requirements of hardware bases, so the models are being trained and we are able to achieve some really good results for, and it could be a really good for business as well, for in both the businesses like in healthcare as well as academics. So that is a really big thing right now. The another part is like the most current advancement in clinical uses and medical image analysis of deep learning research is covered in of the like we are covering current issues, offered potential fixes, and the directions for the future. Moreover, we are going to see like what are current state of the art technologies, how are they working, what methodologies they are using, what kind of outputs we are getting, how much accurate they are, and also like what could be done to increase the accuracy and potential of them in a wide range, to use it in a wide range. Along with that, this is from a review paper. Like this article, the entire PPT and chapter are being taken from a review paper. Based upon that, the sources from that that will be covered later on. The right now, as we can see, like the modern medical uses particularly address the neurological. Like we are basically function mostly concerned about four of the things in human body that are neurological, that is related to brain, cardiovascular, that is related to heart, digestive, that is related to stomach, and skeletal systems that can majorly bone systems, that as well as other important human body part systems. One of the potential breakthrough in this field in the future is the development of technologies that can reduce the heavy demands of high quality large scale data sets. um, so why do we need like what is the use and what is the purpose of this particular article? It is that because the utilization of artificial intelligence software to extract medical data has grown significantly in the healthcare business as a result of fast advancements in the AI technology. Also, one of the crucial components of medical assessments and judgment is the interpretation of medical images, which has become a focus of active study in both industries and universities. Right now, our doctors are really very well trained, and to see the mumps or lesions or anything in a MRI or CT scan or any of the like medical images that we go through, so that they could understand and detect out any of the like um, disease or any problems that are going on with our body, or anything. With the use of artificial intelligence, we would be able to scale or like find out the even the slightest of the let's say swollen or any of the parts in your medical image. It won't go like undetected by that, if once it is 100% completely working, then it would be even more better, and the risk of human lives would be reduced a lot by these technologies. So the deep learning has recently been used in analysis of medical images to perform a number of computer vision jobs, including classification, detection, segmentation, and registration. So classification, detection, and segmentation are among the most important and typical activities, since there several cutting edge works have been offered in the rapid developing scientific field of deep learning. Now, with thorough and complete clinical study, we evaluate the most recent advancement in the medical field of the medical image analysis in this particular paper, the review paper that I was previously talking about. Next are the state-of-the-art methods that are currently used for all these particular methods. So different medical imaging modalities have their unique characteristics and different responses to human body structure and organ tissue, and can be used in different clinical purposes. There are four tasks in which our various state-of-the-art models are described as follows. First is image classifications. The preeminent categorization tool for picture assessment is the convolution neural network. The CNNs are the neural networks in which perform way better than any other neural network like RNNs or any other. They provide the best results currently, when it comes to working with pixels or images. So the CNN architecture has constantly evolved as deep learning has progressed. Now, the original CNN AlexNet was made up of many convolutions that were each succeeded by a max pooling function, ReLU, and ReLU is the activation function here, in which the portion is considered as zero, like any negative negation, and a positive number. So it forms a line, and then it is a step for downsampling. Also, the F1 score is used to calculate its accuracy. It used 3 cross 3 convolution kernels and 2 cross 2 maximum pooling to simplify the structure of AlexNet. And some of the most popular CNN-based categorization network topologies are shown in the figure on next slide. So these are the images of the most current networks that are there for as you can see, image classification in the market right now, that are VGG, Inception, DenseNet, namely. Moreover, there is another important part of like image class medical image analysis is object detection. In the medical detection, frequency of aims to find patients indication of abnormalities. We try to find any abnormality in their X-ray, CT scan, MRI report, anywhere. So to find that is really important. For example, like lung nodule detection in chest X-rays or CT scan, and lesion detection in CT images, and mammography lesion detection are examples of clinical use of detection tasks. For that, like there are really two well-known and popular single-state detectors with straightforward model designs are the YOLO family and single-shot multi-box detector, shortly called as SSD. Both architectures are built on feed-forward convolution networks, and it will be shown in the next slide how the model or the architecture looks like. And the other two images that are illustrates the CORNET and FastNet RCNN object detection working mechanism, and the accuracy is calculated using the MAP formula, that is mean. Uh, Sorry. So YOLO is the one of the models. As you can see here, there are multiple layers that are there, and in the end, we are getting classification or bounding box by regression. Similarly, for SSD, it is given like how classification and box regression is there. There are multiple layers. One is horizontally, second one is working as a vertical layer for predicting and everything. So these are the examples of object detection frameworks. Next part is image segmentation. The goal of image segmentation was to identify the shape of an organ or other anatomical feature in an image. So the segmentation of various organs or organ structures such as like entire heart and pancreas, tumors and lesions such as the liver and liver tumor across several medical image modalities are among the segmentation tasks used in clinical applications. So the most often used FCN for medical picture segmentation is the unit design. So this is the on the right hand side you would be able to see the unit design, that is like firstly image is given, then we downsample it, and after multiple stages of downsample, it is like a feed to the convolution module, and then the convolution module understands it and it upsamples it, and finally the masking is done. So that is how the entire process works here. The most often used FCN for medical picture, that is unit, and it is like expansive path of unit is explained here. uh, Next part is like what are the clinical applications for these models that are proposed here. So there are multiple papers or studies suggesting that like a technique for image pre-processing that would normalize 3D volumetric scans by Dr. Singh using an intensity profile in order to enhance the 3D CNN based acute brain hemorrhage detection, and it was like on by the best F1 scores on the CQ500. It was tested on CQ500 dataset, and based upon the F1 scores, the accuracy were around 96%, 93, 98, and 99 percentage respectively for subarachnoid, intraparacemal, subdural, and intraventricular. And similarly, this was for brain hemorrhage, and after that for heart diseases like cardiac CT, Dr. Zhang developed an end-to-end learning system for identifying coronary calcification in specific arteries that may immediate procedure accurate test results based upon provided CT data. It was by using the method of cross validation. It was tested on 169 non-contrast cardiac CT scans, and it was operated from two centers. It was successful in detecting the numbers of classifications with a sensitivity of 90.5% and the volumes of calcification with a sensitivity of 93.3% and a PPV of 96 percentage, as mentioned. Also, as you can see here, based upon the uh, yeah, one interesting thing to note down is like the data is really nice. Like 169, it was tested on 169 non-contrast cardiac CT scans, which was was able to obtain from two centers. So to collect data from uh, for medical image analysis, that is a really big task or a challenge in itself, because that is something really classified information for patients and for the medical team. So that is something we will further talk upon. But that is a one main challenge that people face while trying to maintain this data sets and everything. Next part is like when Zen introduced a deep learning based liver tumor classification system that was trained using 1210 cases and verified in 201 patients with an OC value of 94.6%, the system can identify that accurately. So as I mentioned earlier, right, like here if you can see 1210 cases, and here 3346 radiographs. This data sets are really very less as compared to what we use regularly used, like there are hundred thousands or a million even, or thousands and thousands or millions, even in millions the data is fed to the model so that they could learn accurately. But to get our hands on that, so the more data we would get, the more accurate the model would be. But still, on the less data, the accuracy of model was 95.5%, and orthopedic surgeons accuracy was 92.2% for hip fractures or any bone related injuries. So based upon that, as you can see, the like model outperform an orthopedic surgeon's accuracy, which was 92.2%. Also the neurological system, like anything related to brain, heart, stomach, or entire digestive system and the bones, are four major systems of human body that are covered in our study for cutting edge therapeutic applications. To be more precise, the discussion focuses on the AI algorithms for medical picture diagnostic analysis for the representative disorders of the brain, heart, and liver, as well as orthopedic damage that has been, if by any chance, has been occurred to the human body. uh, Challenges and future discussions. So, as I mentioned earlier, there small scale medical data sets continue to be the key barrier in this discipline, despite the fact that deep learning models have had considerable success in the interpretation of medical picture data. As I talked earlier, again, the another big challenge would be the domain transfer, which adapts a model learned on natural images to medical image applications or from one image modality to another is one approach that could be used. What could that this thing could be done for this particular challenge, and in future to overcome this barrier. This approach is inspired by transfer learning technique, and another approach is used to federated learning, which enables cooperative training across various data centers. And another significant issue with medical image is class imbalance. Numerous studies on novel loss function designs, including triplet loss, contrastive loss, grading loss, and focus loss, have been proposed to address this issue. So, class imbalance is something like there is a lot of data for brain and how you are defining your classes, so there would be a lot of data for particular class and very my few data and for any other classes to fill into. So this way your model won't be learning in a particular manner. So like based upon that we can tune our parameters by using the losses of gradient, focal, or contrastive, and we can deal with this issue. Another approach is to draw subject matter expertise in this particular domain. So that is something that could also be done. And future directions are uh, also being mentioned as for this particular portion. Let's finally the conclusion. The development of cutting edge deep learning techniques has made medical image analysis extremely successful with excellent accuracy, efficient, and stability. Also, scalability is there. Now, we examined most of the recent developments in CNN-based deep learning algorithms for clinical applications such as image classification, object recognition, segmentation, and registration. The brain system, brain, heart, stomach, and the bones were studying along with more in-depth image analysis-based diagnostic applications. More specifically, cutting-edge research for various illness such as brain, cardiac, and liver ailments, as well as orthopedic trauma is presented. Also, this study we discussed the issues that are currently plaguing the subject and offer potential fixes as well as future research prospects. So that's it from the reference link is given here in the portion, and that's it from my side for this particular study. So thank you for your time and for going over this particular part, and I wish you a good one.